and close. So thank you very much. Today is lecture 11, which essentially we go from electrostatic to magnetostatic, and that's really historically very nice. And magnetic field also by itself is very interesting. And today you will see some of those interesting, let's say, concepts that we do have in magnetostatic. So, so far, what we discussed, we considered that the charges are not moving in space. So we have a specific charge distribution in space, and then we do have boundary condition, which this boundary condition can be due to specific charge distributions, can be due to, let's say, different material. And what we found, how to solve Laplace equation and Poisson equation there with the proper boundary conditions, and finding potential, and from the potential we got the electric field, and from the electric field we know what's going on with the force, and doing the dynamics and understanding the motion of an object. Okay, now we go to a different form which historically thought to be completely a new force, right? And I'm sure that as physicists, as a graduate physicist, you know that we have four forces in nature, which is electromagnetism, gravity, weak interaction, and strong interaction, okay? Or weak force and strong force. So we don't talk about the last two, we talk only about the first one and the second one. Second one, which is a gravity by itself, is also is a big challenge. When we talk about electromagnetism, essentially more than 90% of the interaction that we daily experience is based on electromagnetism. And historically, they thought that we have electricity and magnetism completely being different disciplines, different research activities. But however, thanks to Maxwell, he showed that electricity and magnetism, they are just the same form. And we will see with a few examples. And but right now, as I say, that historically we are going with that approach. So people, they maybe in the same time, or maybe almost the same era, they find that they deal also with the magnetism. And we know very well that the capacitor people they use to find the direction is based on a magnetic dipole, and essentially based on the orientation, you can find the North Pole and the South Pole. Okay, so what people they find out at that time, that if you have one of those dipoles, which is essentially either is a needle or a magnet, which you can find it in nature, then you will see that you will feeling a torque, which this torque essentially is given by the magnetic dipole or magnetic moment of the material multiplied by the magnetic field, or if I want to be very careful, I have to say that that's a magnetic flux density. Okay, so magnetic flux density, or even sometimes they call it magnetic induction. So the concept was like that. So you have magnetic field or this magnetic flux density everywhere, and then you place a dipole here with mu, and then this mu starts to, and the magnetic field starts to introduce a torque and moving or rotating this object around. And based on that, you will find the direction. And that was essentially the source that people, they use the magnetic field and they deal with the magnetic field. So My apologies if I'm using the magnetic field. It's just I'm addressing explicitly the magnetic flood density. Okay. When it comes to writing an article, I will be very careful in writing magnetic flood density or magnetic induction. So we have to be a little bit careful and understanding these a little bit better. So here we are not dealing, I mean, of course, when we are talking about magnetic dipole, it's a little bit tricky, and you will see towards the ends of this lecture what I mean by that. But at the beginning, let's consider that we are talking about moving charges, okay? And these charges are moving with velocity way smaller than velocity of the speed of light, and they are moving in a uniform fashion, okay? So if you consider this, indeed, we could assume that we have specific volume in space, and I define a quantity which I call it the current density. Current density, which tells me how what's going on, and the current density is in unit of, let's say, charge per time per surface, okay, or per area. So indeed, if you want to look at the dimension will be either ampere per meter square, or you can say coulomb per second per meter square, okay, in the SI unit. So indeed, that shows that if, for example, I have a J, specific way, specific fashion, again, J, and I consider a specific volume, which is embedded by a surface, then due to these currents that I have, then I'm expecting the total charge inside of these, let's say, volume will change, because, for example, if the currents are coming inside, and let's say that the density coming inside is different from the density going outside, then I'm expecting that charge will accumulate inside of this volume. All right. So it's look like, let's say, looking at the spring, and you will see that the spring, the water comes out, and then if you consider, let's say, certain volume, the volume of water inside of these, let's say, surface or embedded surface always is constant. However, when it comes to the source of the spring, you will see completely different scenario. You will see that water is coming also always outside. So the water will be outside of this, let's say, surface. So indeed, that's exactly the same scenario. We are talking about the source of the current, okay? Here. So if you assume that's volume, which is given, then we say that due to the current that we do have current density, which you may have at different regions, we assume that at the let's say azimuthal surface there is no current, and the current is going only from surface 1 to surface 2. Then what I'm expecting, that if the currents are different, the current density are different, then I'm expecting that the charge will accumulate inside. Will be accumulating. Or if I want to be very careful, I would say that the rate of the current will change. And since we are talking about current, rate of charge density will change. Since we are talking about volume, we are associating a charge density here. And this charge density, indeed, if these J's are different, definitely they will change upon time. All right, is that clear? So then the rate, how can we calculate the rate? The calculating rate will be how much current they are coming inside and how much current they are going outside. Essentially, what we need to do is doing the integral of J dot N for all surfaces that we do have. That will show to us that what's going on with the J dot N, which is essentially multiplied by the surface, that will be the current that's coming inside of this, let's say, volume. And that will show us the rate of charge density. So if J dot N integrating on all surfaces is equal to 0, I'm not expecting the charge density inside of this volume will change. So always these will be a constant value. So if I want to show that, that essentially is given by time derivative of the charge density. All right. Yes or no? Okay, let's see. So let me give you a calculation and see that this is not correct, because J dot N, what is the quantity? I just showed here. J dot N dot sigma is a charge per second per area multiplied by area. Area goes away, that will be charge per second. So that should be C. That's the rate of total charge, not the charge density. Is that clear? Good. So indeed, integral of J dot N ds is equal to the time derivative of the total current, or let's say the total charges, which is derivative of the Q inside of that volume. So how do we calculate the total charge inside this surface? We do the integral of rho d volume, which the volume that is created by that surface. So indeed, that will be time derivative of integral of rho d volume. And then we can use the Gauss theorem, and that will be integral of divergence of J d volume on the volume V, and that is equal to integral of rho d volume time derivative. So I will stop here and I will talk about the physics, that what's going on here. So if the currents are coming inside, what do you expect? So look at the direction of J dot N. N is outside, right? If you have a surface, N is normal to the surface, which is outside. And J, when it's coming in, you are expecting the charge inside will be increasing. So J dot N will be negative indeed. So for J dot N, which they are opposite direction, then you are expecting the charge inside of the volume will be increased. When going for the opposite side, if you assume that the J, the current density, is going outside, then you are expecting the charge inside of the volume will be decreased because more charges are going outside, right? So then next time you will have less charges, and less charges. So there is a negative sign to assign here, just to associate that this n is a normal to the surface towards outside of the let's say the surface that you do have it there. Okay, so I will put the negative sign here. Now I will put them together, and that is applied for any volume that you created. So integral of the volume of divergence of J plus the time derivative of rho dV is equal to 0. And that is true for any volume that we assume. Therefore, we reach to this equation, which is the divergence of J plus time derivative of rho is equal to 0. We call this continuity equation, which will tell us that the charge and the current, they have a relationship together. And the charge are, the number of charges in space and time is constant. So if you have a specific charge distribution, if you move them around, you're creating a current. But remember that the current has a relationship with the density of the charge distribution. All right? Is that clear? And this continuity also is true for in many different parts of physics. For example, if you talk about continuity in the mass or continuity in the fluid dynamics, and etc. So that is something that we have to be very careful when we are handling. So now I know that if the charge density is changing upon the time, I'm expecting the divergence of J to not be 0, right? So far previously, what we assumed that the rho is constant upon the time. If rho is constant, definitely divergence of J is equal to 0. All right, this is what we talk about electrostatic regime. And now we are considering different scenario when rho is a function of time as well. Okay, and as I'm emphasizing again, guys, that the velocity that you associate to the charges, and the charges are moving around, is way smaller than the speed of light. Okay, this is necessary. Else, I mean, in the electrodynamics too, usually I teach that. So when you want to go with a velocity which is close to the velocity of c, or let's say a fraction of that, then you have to do the retardation and retarding the potential and doing the mathematics and doing the calculation. And we have to be very extremely careful. We have to be extremely careful with those sort of calculation. Then we have to be very careful. I mean, I'm not talking about the retarded potential. And if you remember, we calculated the scalar potential, which was 1 divided by 4 pi epsilon 0 integral of rho of x divided by x minus x0 and x prime, d3 of x prime. So now, if we assume that rho, which is not only function of, let's say, space, but also is a function of the time. So rho, in this assumption that we do have, that is not only function of x prime, but also function of t, what you want to do with that? Will you simply just replace t here, and then you make the potential as a function of t? You know what I mean? Are you allowed to do that? No, we are not allowed to do that easily. So we have to do a little bit of calculation, and because the charge distribution that you do have here will create a potential with a delay. And this delay is given by, let's say, the force that we discussed, the speed of the force, essentially, the virtual particle, which is photon for electromagnetism. And that is traveling with the speed of c in vacuum. Okay, so whatever you place there in the charge, when you assume it, will affect the potential and the position of x with a delay of x, let's say x minus x prime divided by c. Okay, so we have to be very, very careful when we are dealing with moving charges. Okay, so I'm not even considering this in this section or this chapter. What we consider, we are talking about a magnetostatic, even we are not talking about the case when they are function of the time. But we have to be very careful, as I say, that the current, when we are talking about divergence of J plus time derivative of rho equal to 0, this continuity equation, we have to be very careful that in order to get the J, which is a function of position, then the time derivative of rho should not be equal to 0. So it seems that rho should be function of the time. Okay. Anyway, so okay. So in general, if I want to say that the J also is a function of time, rho also is a function of time. Okay. But this is the electrostatic that we consider. We assume that the J also is not a function of time. All right, perfect. So then people, I mean, historically speaking, when people, they look at a magnetic field, apart from this talk that they have seen, I think it was Biot-Savart, I mean, these two scientists, Biot and Savart, which they look at the calculation of the magnetic field due to a current in the space. So you do have a current in a space, and for simplicity, we assume that this current is given on a line, so which this line is dl, on a specific, let's say, line, because usually we deal with wires or circuits. And then they want to understand what's going on with the magnetic field in a point of observation of P, which the distance between this the wire and that one is about x. Okay. And they say that for these small elements here, which we do have the current of I and the small element is dl, then the magnetic field at that place, or let's say magnetic flux density at that given place of x is given by a constant, then multiplied by the current times dl, okay, multiplied by the distance, which is x, divided by x power of 3. So that was the formula that they had it at that time. It was empirical. There were no derivation in it, like the column, essentially, that we had. And remember that the magnetic field, if you look at the magnitude of the magnetic field, it seems that it's going to be 1 divided by x power of 2. So it's 1 divided by r power of 2, which it seems that it's following the same relationship that we had it for the Coulomb potential. Okay, it's going with it's a square root 1 divided by r power of 2 field. So, and this k exactly look like the Coulomb Coulomb's law. This k, depending on the system that we use, so SI units or doing CGS or electrostatic one, this k can have different quantity. Okay, for example, in SI is mere 0 divided by 4 pi, while in the CGS and in the electrostatic one is 1 divided by c. Okay, which somehow, as I say that during the first lectures, I really love the electrostatic unit, because the electric and magnetic field, they have the same magnitude and it's very easy to handle. So that was found by Biot-Savart way back, and they formulated this. And indeed, if you want to calculate what's going on with the total magnetic field at any point of P, which what we consider, then you have to do the integration along that line, which essentially we do have it, which is integral of I dl cross x divided by x power of 3. Okay, and that's on the line that we do have. Is that clear? Good. Even if you want to make it more complicated, then you have the permission to do that. So essentially, you can say that the point that we are looking at, that the current or the element of the current is given by x prime, and that one is given by x, then that distance is x minus x prime. And therefore, if you want to calculate the b at the point of x, you have to do the calculation of mu0 divided by 4 pi integral of I dl multiplied by x minus x prime divided by x minus x prime power of 3. Okay. Good. So that was clear for a wire, but if you have a current density of J, what you have to do, you have to replace this with a J d3 of x prime. Okay. And if it's a surface, it should be k dot d sigma, called k d d2 of x prime. So remember that. So whenever it comes to doing the calculation for the current density, then we have to replace it with a J d volume. All right. We have to be a little bit careful again, so that some people may be naively thinking that dl times the current can be replaced by dq, but be careful, this is completely wrong. This is this is well discussed inside of your book. So what is proper is that IDL should be replaced by J d3 of x prime in the case when you want to do the calculation for the current density. A B field, or let's say B flux density, essentially, the unit that you do have for it is Newton ampere meter. Okay. Look like what we do have it for electric field. If you remember, the electric field was given by Newton per coulomb. Okay. So in terms of magnitude, it seems that speed of light multiplied by B has the same unit as the electric field. Okay, so the unit of CB is equal to the unit of electric field, which you will see that from Maxwell equation when you do the calculation for total energy density. So you will see that appears in the calculation. And also when you solve Maxwell equation for vacuum, you will see that there is a relation between E and B, which that is given by this coefficient of C. All right. So for example, I can use this formula of Biot-Savart and doing the calculation and understanding what's going on with magnetic field of a wire. So assuming that I do have a wire in space, which has a current of I in a specific direction, which assuming that this direction is Z, and then I want to find out what's going on with the magnetic field at the distance of, let's say, R here. So I can choose the coordinate of XY. So that is X direction. That's a point of observation. Then any elements that I consider here, the distance between these two will be square root of R squared plus Z squared that you do have. And essentially using the Biot-Savart law, B at the point of, let's say, P will be calculated based on mu0 divided by 4 pi integral of I dl, which the dl is along Z direction. So it will be Z hat dz cross the distance, which is that distance essentially. So which will be, let's call it is okay. Minus Z, let's say in this way. X hat minus Z hat divided by, sorry, that should be R squared plus Z power of 2 power of 3 divided by 2. Okay. And the integral will happen for dz from minus infinity to plus infinity. So that will be mu0 divided by 4 pi. So along Z is completely symmetric. So along Z direction, there will be no magnetic field. What happens, it will be the only term that plays role, it will be the other term. So it will be mu0 I R integral of minus infinity to plus infinity of dz, then it will be Z hat cross X hat divided by R squared plus Z power of 2, 3 divided by 2. So Z hat cross X hat, so we know that they form a right angle, so it will be X, Y, Z. So Z cross X will be Y hat, and that will be mu0 4 pi I R Y hat integral of minus infinity to plus infinity of dz divided by R squared plus Z squared power of 3 divided by 2. Okay. Which the value for this, someone of course can, if I want to solve that, Z divided by R, I will consider it as a tangent of, let me see, the tangent is better. Yes, let's consider that tangent of theta. Okay. Can someone do the calculation, guys? Or should I use the Wolfram alpha? But if you choose Z divided by R as a tangent of theta, you can solve this integral. But I don't want to spend time on this. Let me see if I have mathematical open. If I do have mathematical open easily, I will do that. Okay. So integrate of 1 divided by A square plus R in Z square and Z from minus infinity to plus infinity. And I assume that A is a real quantity, 3 divided by 2. So it seems to me is, okay. Assuming A is positive and A is element of real. That is given by 2 divided by r squared. So that will be mu0 divided by 4 pi I y hat divided by it multiplied by 2 divided by r. So that will be essentially mu0 divided by 2 pi I divided by r y hat. So for a wire, essentially the magnetic field that you will see at the given point, it will be given by the current divided by the distance that you do have it from the wire, and is along y direction. Or if you assume that the current is going up and the point of observation is along x, that will be based on z cross x, or along this way. I mean, going with the right hand relation. So your thumb is along the current direction, and then the magnetic field will be given by the 4 hands. Yeah. So perfect. So, but I mean, if you look at this formula, it's somehow it's similar to the electric field that we do have for a uniform line of charges. If you have a line of a charge, then if you look at and doing the calculation for electric field, you will see that is given by 1 divided by r. So that also the electric field was given by 1 divided by r here. Of course, there was a coefficient which was the charge density, which was lambda in the calculation, and epsilon 0 as well was given in the calculation. But we have to be very, very careful when we are talking about magnetic field. That may fool us that electric field and magnetic field, they are identical in this sense, but no. Maybe in terms of mathematics, they will show up in similar fashion, but in terms of nature, if you do the calculation, you will see that there is a corresponding between them, but we have to be very, very careful with handling the mathematics. So it almost at the same time as Biot-Savart, Ampere did a calculation and did a couple of experiments and look for what's going on with the force due to the magnetic field. Magnetic field, or what I call it, magnetic flux density. So what he looked into, he had, let's say, a circuit, or let's say wires, and another wire, and he looked at the calculation, or he looked into the force that wire number 2 introduced into number 1 and wire number 1. So wire number 2 introducing a force to the wire number 1. So the aim that he had was looking for the force due to the wire number 2 on wire number 1. And of course, that's a vector. So what he came up with that, he said that, okay, the element of this force is given by essentially the current that I have in the wire 1, and I'm doing this calculation for a force which is for the element of the L1, And wire number 2, or the circuit number 2, is creating a magnetic field here. And this magnetic field is given by B. And he said that the force essentially due to the circuit number 2 on circuit number 1, element of circuit number 1 is given by I1 dL1 multiplied by the magnetic field from circuit number 2 at the position of number 1. Okay, is that clear? And we did the calculation right now that due to the Biot-Savart law, B essentially can be given by the above expression that we had. That one, which is I2 dL2 multiplied by the distance between the two, which is x minus x prime. All right, is that clear? So that's the force that we are expecting. So due to any elements that we do have here and the distance that we do see here, there will be a magnetic field induced there. And this magnetic field essentially is given by mu0 divided by 4 pi epsilon, 4 pi. And then we have I2 dL2 cross the distance between circuit number 1 and circuit number 2. So essentially that will be x1 minus x2 divided by x1 minus x2 power of 3. And what I mean by x1 and x2, that's x2, and that is x1, which is the position of those infinitely small elements on circuit number 1 and number 2. Good? Nazanin, do you have a question?
Shouldn't there be an integral over dL2?
Absolutely, absolutely. We will do that. I'm just doing, that was only due to a small element. But if you want to do for the entire the circuit number 2, what we have to do, we have to do the integration on circuit number 2. And that will be the total magnetic field at that small region. Okay, is that clear? If it's not clear, just let me know. We may just erase the figure and explain it in a better way. Good, thumbs up. Oh, okay, perfect. So then that's really the force on infinitely small element on the circuit number 1 due to the circuit number 2. So that will be I1 dL1 cross mu0 4 pi integral of on the circuit number 2, which is a closed circuit, by the way, I2 dL2 cross x1 minus x2 divided by x1 minus x2 power of 3. If we want to do the calculation and finding out what is the total force due to the circuit number 2 on circuit number 1, what we have to do? We have to do integration on the circuit number 1. So the total force from circuit number 2 on circuit number 1 will be equal to mu0 divided by 4 pi I1, I2. Oh, let me keep them because I would prefer to go with a general statement, and then later on we will do that. Integration on circuit number 1. I will go with I1 dL1 cross. I'm writing ugly. Okay. Integral of circuit number 1, integral on the circuit number 2. That will be I1 dL1 cross I2 dL2 cross x1 minus x2. Okay, divided by x1 minus x2 power of 3. Good. All right. What I have, I mean, I could write it in a different way, but why I have written in this form, because I want to tell you that if you are not dealing with wires, which is you have a current I1 times DL1, if you are dealing with current density, then these two will be replaced by the current density. So essentially, in general, if you want to write a general formula, that will be mu 0 divided by 4 pi integral on, let's say, region number 1 and region number 2, and then you do have J1 D3 x1 cross J2 D3 x2 cross x1 minus x2 divided by x1 minus x2 power of 3. Okay, so essentially these two, they are replaced by the current densities. Okay, so but however, for this case that we are dealing with, for the current case, we are assuming that currents are uniform, then we can take them out. So it will be mu 0 I1 I2 divided by 4 pi integral of on the circuit number 1 integral on the circuit number 2, so which is a closed loop, by the way. It will be DL1 cross DL2 cross x1 minus x2. In your book, for simplicity, Jackson has written x1 minus x2 as x12, just to keep it for simple. So we have cross product of 3 vectors, and we want to simplify this. How we should do that? So it will be, we use the backup law. So it's A cross B cross C. That will be back cap. Okay, so DL1 cross DL2 cross x12, that will be equal to DL2 DL1 dot x12 minus cap, which is x12 DL1 dot DL2. Good. All right. Perfect. So then the force from circuit number 1 to 2 is mu 0 I1 I2 divided by 4 pi. And we do have 2 terms. So essentially we have integral of DL2 DL1 dot x12 divided by x12 power of 3 minus 1, 2 DL1 dot DL2 x12 divided by x12 power of 3. Okay, So what it will be the result of the first one? Two people, they disappear, by the way. What will be the result of first one? The integration happens on a loop, remember that. Integral of dx on a loop, what it will be the result? 0. So for the first one, that will be integral on dl1 dot x2. So there will be, these two, they are completely separated. So dl2 and dl1, they will be separated. So if you do the integration on that, you will see that this is equal to 0. Okay? And the only term that remains is the second term. So that will be minus mu 0, I1, I2 divided by 4 pi, integral of circuit number 1, number 2, x12 divided by, oh, let's write it in the proper way. That will be dl1 dot dl2 multiplied by x1 minus x2 divided by x1 minus x2 power of 2.
Sorry, can you explain, please, why the first term is 0 again?
Look at the integration of dl1 dot x1 minus x2, okay?
Mm-hmm.
And what about the other one? dl2. All right. So this is what we are dealing with. x12 power of 2. Is that right?
Yes.
Okay. So let's, the first term considered is dl1, dl2, okay? And the second one will be, for example, it's, you have 3 components essentially. So it will be dlx times x1 minus x2, all right, divided by square root of whatever you do have it, power of 3 divided by 2. Then you have another component, which is dl y1 minus y2. Oops. Okay, got that. Sorry. So y2 that is power of 3 divided by 2 plus dlz z1 minus z2 and divided by that 3 power of 2. All right. Do you agree on that? How dlx, dly, dlz, they will change is on the circuit. You start from a point, you end up there again. So it will be from a point there to a point there. So what does it mean that if you have a circuit? So it means that if you have dx, it means that that's integral of minus x0 to plus let's say an x0 to an x0. Yeah. So all of those terms, they will be equal to 0 because you are starting from a point and you end up in the same point. That will be the value there minus the value at the same place.
Yeah, thank you very much.
Okay, good, of course. Now let's look at the calculation for the previous example that I do have two wires. Both of them, they have the current of I1 and I2. And the distance between them is R, okay? We did a calculation previously, and what we found that the magnetic field here is given by mu0 divided by 2 pi I1 divided, let's say, let's go with this framework notation. This one is I2, that one, the previous one was that is I1, the previous one was I2. So we got I2 divided by R. All right. This was the magnetic field at this place. Do you agree? And what was the direction of the magnetic field? Was along Y direction. If you assume that is Z, that is X, definitely the magnetic field was along Y direction. Okay. Then, without going into the calculation of these, we can calculate what is the force there. So if you do the calculation of the force, you will find out the force is given by minus mu0 divided by minus mu0 divided by 2 pi I1 I2 divided by R. All right. So let me do them a little bit of mathematics. Let's just see that. So the force will be integral of I1 multiplied dl1 multiplied by b. So, and that is given by I1 I2 mu0 divided by 2 pi integral of dl, which is z dz. Good, because there is some important point here. So let's go with this one. df is given by that, dz, and what else? That will be an r here. Okay. So df with dz will be equal to I1 I2 mu0 divided by 2 pi 1 divided by r along z direction. Along z direction, that will be z cross the b field, which was y hat. Okay, z cross y hat. So z cross y hat will be minus I1 I2 divided by r mu0 divided by 2 pi, and that will be along x direction. Okay. So df, the force per unit length that we do have, which is dz, per unit of length of this wire, essentially is given by minus mu0 divided by 2 pi I1 I2 divided by r, which is the distance, multiplied by the unit vector of x hat. So it shows that if the two currents, they are in the same direction, then the force that the wires they feel, it will be attractive. So they are attracting to each other. While if you go with the negative one, let's say opposite directions, then the force will be positive. So it means that it's repelling the two wires from each other. So the force is proportional to inverse of the distance. So if you keep them closer to each other, the force will be higher. If you keep them far away from each other, the force will be lower. If you have more currents, then the force also will increase further and further. Okay, so that's really, really an important, let's say, observation that people they see it, and including Ampere at that time. So Ampere shows this effect in laboratory. No, the accent is the opposite way. So I hope that you do have a little bit of clear picture about what's going on with magnetic field. However, remember that essentially in laboratory, I mean, in theoretical calculations, and essentially going with comparing to electrostatic, we really didn't care too much about the electric field. We usually care about the potential because it was way easier to drive the electric field from a potential. And same scenario happens here. So of course, the magnetic field that we can observe it as point of x was given by mu0 divided by 4 pi, and that was given in terms of j. So it was j, well, let's write it in this way, d3 of x prime, j of x prime multiplied by x minus x prime divided by x minus x prime. So that was the force that the magnetic field, the magnetic flux densities that we understood. We got it from a specific current density in the space. And remember, the current is time independent, so it's fixed, it's not changing upon the time. So that was the observation that we had. And comparing that to the electric field, if you remember, the electric field at the point of x was given by 1 divided by 4 pi epsilon 0 integral of d3 of x prime. And for electric field was charge with density, which was rho of x prime. And then we had x minus x prime divided by x minus x prime power of 3. Remember, that was the electric field, was not the potential, okay? And from this, what we obtained the divergence of E, which was given by rho divided by epsilon 0. And also we had curl of E for the electrostatic, which was 0. And from this one, we obtain a potential. Usually we deal with a potential. And we say that electric field is given in terms of given by the potential minus gradient of potential. Now we are going also to derive similar expression. Similar expressions for B. So we want to calculate what's going on with the divergence of B, and we want to calculate what's going on with the curl of B. And hopefully, we define a potential. Because dealing with the potential is way, way easier than dealing with the field by itself. Okay? Remember that the nature of electric field and magnetic field also, they are different in another sense. I mean, of course, they are the same nature, but in terms of mathematics, they are a little bit different, because here the force was given by Q times E, and here force was given by, I'm writing in terms of this, so J cross B d3 of x prime. Okay? So in this, those are the differences that you have to see. That the force is given by the cross product. Here is a scalar, which is scaling only the magnitude of the electric field. Okay? Is that good so far? Fantastic. Do you want to have a rest and then coming back? I see that from you that you are a little bit okay. Have about 10 minutes. Is that fine? 4 or 5. I will see you. So, welcome back. Now, our goal is finding the divergence of B and curl of B from, explicitly speaking, Biot-Savart law. And let's start from let's start to reform the above expression, so which is B of x is equal to mu0 divided by 4 pi integral of d3 x prime j of x prime cross x minus x prime divided by x minus x prime part of 2. So let's calculate curl of when I write curl without prime, I mean that the derivative will happen with respect to x. Okay, without a prime. Okay, curl of j x prime cross one divided by x minus x prime. Let's see what we will get from this. So when we write curl of a vector time a scalar, so essentially that's the formula. So is curl of a vector, which is a constant vector, I will call it A, times a scalar, which the scalar has the functionality of x. All right. So remember, x and j is constant with respect to x, and this only is the variable. Okay. So I look for the I components, that will be epsilon I j k, derivative with respect to j of that scalar, which will be in the vector, which will be jk of 1 divided by x minus x prime. All right, do you agree? Perfect. So that will be epsilon I j k. Then the derivative will happen with respect to the other term, which will be j k, or let's write it in this way. One divided by x minus x prime. Then I do have jk. So derivative with respect to j of x minus x prime, what it will be the value? So derivative with respect to xj of x1 minus x prime 1 power of 2 plus x2 minus x prime 2 power of 2 plus x3 minus x prime 3 power of 2 power of 1/2 with a negative sign. This is what we are looking for. True. So that will be minus 1/2. And the other one will be 2. Derivative with respect to x happens. So that will be x I minus, no, let's say xj minus x prime j divided by x minus x prime power of 3. You agree? Okay. So 2 goes away. That will be minus xj minus x prime j divided by x minus x prime power of 2. So the above expression then will be minus epsilon I j k then I do have xj minus x prime j divided by x minus x prime power of 3 jk. Agreed? Which means that that will be minus x minus x prime divided by x minus x prime power of 3 cross j of x prime, I component. Good? That's the I component of that cross. So, but since there is a minus sign here, I can swap vector j and x minus x prime divided by x minus x prime power of 3. So I will get j cross x minus x prime divided by x minus x prime power of 3. I component. So indeed, I found an identity, which the identity is that curl of j of x prime divided by x minus x prime is equal to j of x prime cross x minus x prime divided by x minus x prime power of 3. All right. So inside of B, instead of j cross x minus x prime divided by x minus x prime power of 3, I will replace it with a curl of j divided by x minus x prime. So therefore, I will get b of x given by mu 0 divided by 4 pi integral of d3 x prime curl of j of x prime divided by x minus x prime. All right. The integral is with respect to x prime and the curl is with respect to x. So I can swap them together. And I assume that this is a well-behaved function. So it's mu 0 divided by 4 pi. Oh, let's write it in this way. Curl of mu 0 divided by 4 pi integral of d3 of x prime j of x prime divided by x minus x prime power of 3. Good? Questions? Can someone tell me what is the divergence of B? Which means that is a divergence of curl of something. Because that's something, right? Is a vector at the end. What is the divergence of a curl? Is 0, indeed. So that's the first expression that we found. So divergence of B from Biot-Savart law will result in 0. Okay? So that's the first expression. Divergence of B is 0. You know the interpretation, so there is no magnetic monopole in the world. That's the meaning. However, note that divergence of B is look like curl of E for electrostatic to be equal to 0. Because that tells us that B can be given by curl of a potential. What is this potential? It's this value. A. And we call these vector potential. A x is equal to mu0 divided by 4 pi integral of d3 of x prime j of x prime divided by x minus x prime. And how do we calculate the magnetic field? Is simply by taking the curl of A, we will get the magnetic field. All right. So the divergence of B, which is 0, will allow us to have a potential, which we call it scalar potential. Is opposite on the other side. For electrostatic, we had the curl of E, which was equal to 0, and then E was given by minus gradient of something, which we call a scalar potential. Here is divergence. Now let's do the mathematics and calculate what's going on with the curl of B. What is the value of curl of B? Nazanin, say something. You are muted.
No, sorry. I was trying to understand in the second line that you've written for B, that should be to the power of 1 x minus x prime, right?
Oh yes, that is 1. Yeah. Thank you.
Sorry,
Thank you.
That's what I was.
Yeah, is a typo. Thank you. So now we want to calculate what's going on with the curl of B.
So it's like curl of curl, and we write it as.
Yes, it will be curl of A. Remember, what is A? Is this quantity. So what is the curl of curl? Again, using the backup, but remember that always the nabla or these two nablas will act on A. So that will be back, which is divergence of A, minus cap, which will be Laplacian of A. Okay. So indeed, what does it mean? That is gradient of divergence of A, which A is, I will take away the mu0 divided by 4 pi, so it will be mu0 divided by 4 pi. And then we do have integral of d3 of x prime, j of x prime divided by x minus x prime. That's the first term. Then we do have another term, which is minus Laplacian of d3 x prime, j of x prime divided by x minus x prime. All right. No mistakes? Yeah. Okay. So now let's do the expansion. So it would be mu0 divided by 4 pi. Then we do have gradient of divergence of that one. Will be gradient of integral of d3 of x prime. Will be divergence of j of x prime divided by x minus x prime. That's the first term. The second term, the Laplacian will act only on denominator because that's the only function of x. J of x prime is not a function of x. So it will be minus integral of d3 of x prime, j of x prime Laplacian of 1 divided by x minus x prime. Agreed? What's that?
Minus 4 pi delta.
Exactly, minus 4 pi delta of x minus x prime. Integrating on x prime will give us, with the minus sign outside, it will be minus 4 pi j of x. Agreed? Okay, beautiful. So indeed, that integral becomes mu 0 divided by 4 pi, then gradient of integral of d3x prime divergence of j of x prime x minus x prime. Then that's the first term. The second term, minus will be positive, so minus multiplied by minus plus. 4 pi goes away, that will be plus mu 0 j of x, which is somehow known to you. So now the point is that let's do the calculation and find out what's going on with this term. Any thoughts? So let's do the same way. We want to do the calculation and we want to calculate what's going on with the divergence of j of x prime divided by x minus x prime. What is that? Is the summation of derivative with respect to x, I, of j I divided by x minus x prime. That's what happened. Agreed? Because it's a vector. Right? So, but remember that j is a function of x prime. So that will be the derivative of a constant, or let's say actually is a constant multiplied by that value. So that will be ji of x prime, which is constant with respect to x prime, xi. Then that will be the derivative with respect to xi of 1 divided by x minus x prime. We already did the calculation for this previously. So that is j of x prime, and that will be x I minus x prime I divided by x minus x prime I. I think there is a minus sign also is needed, because it will be minus 1/2, then it will be 2 multiplied by that one, so it will be minus sign. Yes. Okay, good. So indeed, if we sum over all of those, that is look like having j, which will be minus, having j of x prime dot product with x minus x prime divided by x minus x prime power of 3. True? Okay. So let me just check. I feel that there should be something else in no, that is correct. Okay. Yeah, perfect. So essentially in your book, they have written in this form minus, I think they have written that one as a gradient essentially. So they have written as a j of x prime dot gradient of 1 divided by x minus x prime. I think maybe that is something that we have to consider it or not. Anyway, let's yeah, that's even better. That's even better because I want to create something new out of this. Okay, so the divergence of j of x prime now is given by x minus x prime, which is j of x prime dot gradient of 1 divided by x minus x prime. Good. We agreed on this. Okay. So now, what else can we do that? I mean, is we know that x minus 1 divided by x minus x prime has a symmetric action. So which means that if you take a gradient of these, is equal to minus gradient with respect to prime of 1 minus x prime. So if you swap them together and taking the gradient, they will be identical with the minus sign. Agreed on this as well or not? Okay, that was one of your exercises. So that will be essentially j of x prime with a negative sign of gradient prime of 1 divided by x minus x prime. The dot product between these two. Good. So the goal that I have is that I don't like to handle these as a divergence with respect to prime. A divergence with respect to x. What I know is divergence with respect to divergence of j with respect to prime, because that's the only things that I know here. So let me write it down. So this term essentially was given by minus j of x prime dot gradient prime of 1 divided by x minus x prime. Now I look at divergence of j of x prime divided by x minus x prime. And I know very well that the result will be divergence of prime of j of x prime divided by x minus x prime plus j of x prime dot gradient of x minus x prime with respect to prime. So that's just expansions of the derivative, and I get these expression. I can take the integral of these two sides with respect to d3 of x prime and bring it to the volume, and using the Gauss theorem, I will get the integral of divergence prime to the surface, which will be j of x prime divided by x minus x prime. The dot n d2 of x prime equal to integral of divergence or prime of j of x prime divided by x minus x prime d3 of x prime plus j integral of j of x prime that gradient prime of 1 divided by x minus x prime d3 of x prime. And that's on a volume, and that is on the surface of that volume. And we assume that, let's say those currents that we do have, they are localized in space. So then the surface can go to infinity. And indeed, that goes with power of r power of 2. And the currents, they are also localized. And that also, which goes essentially with 1 divided by r power of 3, the entire of this argument here that we do have. Because the currents are entirely localized, and we know that if the current is localized, the current density is localized, then that it will be extremely small. So indeed, that entire of the integration on the surface will tend to 0 if r goes to infinity. Okay, for large distances. Therefore, from this expression, what I will get that integral of divergence of x divided by x minus x prime d3 of x prime, which I will keep it in the same place, and I will bring the other one to the other side, is equal to minus integral of j of x prime dot gradient prime of 1 divided by x minus x prime d3 of x prime, and both on volume. So indeed, the second term will be simplified and will be given by, so we were calculating curl of B. The first term was mu0 j of x. The second one was mu0 divided by 4 pi gradient of that was integral of divergence, of j of x prime divided by x minus x prime. And we just proved that divergence of j x prime divided by x minus x prime is equal to this. And we already also showed that the integral of this is equal to that value. So we are substituting them here, and we will get mu0 j of x is equal to plus mu0 divided by 4 pi gradient of integral of d3 of x prime. That will be the divergence of j of x prime divided by x minus x prime. So, sorry, it was a little bit long, and you have to follow all of those calculus. So curl of B indeed is equal to mu0 j of x if that term is 0, which is true because we assume that the divergence of j plus is equal to minus time derivative of charge density. If we assume that we do have magnetostatic, then this term is equal to 0 and does not play anything in our calculation. Okay. However, you may say, no, I assume that the charges are moving around, so the charge distribution are changing in space. Then what is happening with that term? essentially I'm only talking about this term now. That can be replaced by mu0 divided by 4 pi gradient of integral of dt of x prime. And I know that from the continuity relationship, I can get time derivative of rho with a negative sign divided by x minus x prime. Okay. I can substitute that here. The time can be outside of the integral, and then what I will get mu0 divided by 4 pi time derivative of gradient of integral of d3 x prime rho divided by x minus x prime. And what is that? Is the potential, scalar potential with a coefficient of 4 pi epsilon naught. So that will be 4 pi epsilon naught of scalar potential. And there is a minus sign, by the way, here. And then that will be, 4 pi goes away, that will be minus mu0 time derivative of gradient of phi with an epsilon 0 at the front. Do you agree? And take the mu0 out, time derivative as well, and that will be, let's say epsilon 0 as well, minus gradient of phi. And that's nothing more than the electric field. And that is mu0, epsilon 0, time derivative of the electric field. So if the charges are moving around, essentially, rho is function of time, then that expression can be modified. And indeed, you will get curl of B is given by mu0 J plus epsilon 0 time derivative of B, which you know as one of the Maxwell equations in your previous lectures or previous courses that you had. Is that clear, guys? Okay. So far, we assume that the time derivative of rho is essentially equal to 0. So we restrict ourselves to the magnetostatics. So essentially, we do have only two relationships. So divergence of B is equal to 0, and curl of B is equal to mu0 J. And from that term, we get A is equal to mu0 divided by 4 pi integral of d3 of x prime J of x prime divided by x minus x prime. And where curl of A will give you the magnetic field. Good. So instead of doing the calculation and finding out the magnetic field, what usually we do, we calculate A, which is vector potential. Vector potential in some senses look like scalar potential because it's, first of all, it's way easier to calculate, and A is related to the current density, while the scalar potential was related to the charge density. So if you compare that to phi was 1 divided by 4 pi epsilon 0 integral of d3 x prime of rho of x prime divided by x minus x prime. So indeed, the source for magnetic field is the current, and source for electric field is the charge. So you see the similarity between the two expressions. And even if you deal with radiation or moving charges and the currents which are time dependent, essentially you are coming and you are trying to modify these two expressions and finding out the retarded potentials before going to calculate magnetic field and electric field. in order to get familiar with A potential, let's do a little bit of calculation and maybe doing that for a few examples. Let's say, for example, for a circuit which is just a loop of current, we can do the calculation, finding out what's the A potential and then what is going on with the magnetic field due to the A potential. Let's do these calculations together, okay? And is there any question, by the way? No? Okay. Good. So remember that these expressions, they are very useful and easy to be handled. So for example, look at the last one. I mean, the curl of B equal to 0 before going to doing some of the calculation equal to mu 0 J. If you remember from Biot-Savart law, we calculate what's going on with the magnetic field of a current, right? A string of current, a line of current, which is what's I, at the distance of R. Here we can use this formula. We can have a loop here. We can have a loop here, which the loop goes counterclockwise. And then we are probing a surface. And we can use this relation, which is a curl of B is equal to mu 0 J, and doing the integral on both sides and doing curl of B dot n d ds is equal to mu 0 integral of J dot n ds. And what we are doing, the surface that we are doing the calculation is this one, and n is this direction that we are assuming. So it's a small element here. And that will be mu 0 total current passing total current passing through these surface, through this surface, which is equal to I, if you assume that that's I. And from the other one, we use the Stokes theorem and bringing B to the line, which is B dot dl, and B there on a distance of R is uniform, so you will get B multiplied by 2 pi R, and essentially that's equal to mu 0. And from here you will get B is equal to mu 0 divided by 2 pi I divided by R. So you see that it's very, very easier to use this formula to find out what's going on with the magnetic field and magnetic flux density. And you can use the right-hand law to find out what's going on with the direction, instead of doing those cross products and doing the integration. It's way, way easier to do that. Now, I just want to tell you that sometimes it's very, very easier to use that relation as soon as we find a symmetry, as soon as you find what's going on with the magnetic field to be constant on a line. If you find that line, it's easy. You make that line, you have a surface, and then you can apply the Stokes theorem there and finding out the magnetic field. Now I will go with a little bit more calculation towards finding the vector potential. So assuming that I have a loop of current, and this loop of current is in a specific direction, so X, Y, Z. So the total current is I, and this is on a ring, which the radius of the ring is about A. Okay. And I'm asking you to find the vector potential. find A. Where? Any point in a space, P. So that's the place of P, which is the point of observation. And that is given in, since the system has cylindrical coordinates, cylindrical symmetry, we can use the cylindrical symmetry, or you can use even spherical coordinate and doing the expansion. Let's do one of those. So the angle is theta. All right, that angle that I assume. And we have to do the calculation for any specific elements here, which is that small element here, which I call it DL, right? And remember, DL is about azimuth angle. So if I want to write DL, DL is given by the element of the length, which is A d phi, right, along E phi. Because it's changing the direction. When it's changing the direction, it means that the vector also is changing. But what is the magnitude of that? If you change by phi, you will see that it's also changing by a d phi. Okay, the magnitude that you do have. In order to be distinguishing phi and phi prime, I have to put a label of prime here, just to make sure that we are doing the integration there. We are not talking about other places, okay? Is that clear? So, good. So what was the relation for A that we had? So A at point of X was given by mu0 divided by 4 pi integral of, d3x prime j of x prime divided by x minus x prime. We can use the same relationship as I say that d3x prime j of x prime is equal to the same that I mentioned, I dl. This is what we do. And dl, we find the dl. So indeed, A of at the point of x is given by mu0 divided by 4 pi integral of A d phi prime and E phi prime divided by x minus x prime. Okay, and what is x prime is that place now. And what is x is this distance. Good. Remember, I have a ring here, and I want to find out what's going on with the vector potential here, or here, or here. As I say that the system holds cylindrical symmetry, so really the point of observation that we choose, the potential there is identical if you rotate the system. Then what I do, I will fix the point of observation to be in the plane of xz. All right, so x indeed, for my calculation, which is the point here, is located in xz plane, which the phi is 0 for it. So what does it mean? That it only has x component and the z component, not y component. And what are the values? So it will be r cosine of theta, right? Z hat plus r sine of theta x hat. And I know that later on I can just do a rotation around that. It's symmetric indeed. I'm not expecting the potential will be different for P, which is in the location in the plane of ZX, or the P, which is located in the plane of ZY. As soon as the distance and the theta they are fixed, they are identical. Good? Okay, that's the symmetry that we do have. And we know that the vector potential will be a vector, and whatever we obtain, later on we can apply a rotation to it and explaining the entire, let's say, plane. Good. And there should be an I as well here, which is I'm missing. What's going on with X prime? X prime instead is located in the XY plane because it's describing the current on a ring. So X prime indeed is given by A cosine of phi prime X hat plus A sine of phi prime Y hat. That's describing the points. And the integration will happen on phi prime, which is changing from 0 to 2 pi. Good? Okay. So let's do the calculation in X minus X prime. We find it, so which is X, it will be A cosine phi prime plus R sine theta X hat. The other one is R, sorry, A sine of phi prime Y hat plus R cosine of theta Z hat. And we deal with the magnitude of that, so which is X minus X prime. I could write it in a different way, but I would like to just write it in a formal. So it will be A squared, A cosine of phi prime plus R sine of theta power of 2 plus A squared sine of phi prime power of 2 plus R squared cosine of theta power of 2 power of 1/2.
Sorry, I think A cosine of phi prime has to have a minus sign. It's like X minus X prime, so it's like.
Why? The X prime is the location of the element.
Yeah, you're calculating X minus X prime, right? The magnitude of.
Oh,
X
yes, sorry. Thank you very
Yeah.
much. Yes, you're right. X is that one. So all phi prime will have a negative sign. Only that term will play a role. Yes, thank you. The other term doesn't matter. Yes, thank you very much. So that will be minus that. Okay. So that will be A squared cosine of phi prime power of 2 plus R squared sine of theta power of 2 minus 2AR cosine of phi prime sine of theta plus A squared sine of phi prime power of 2 plus R squared cosine of theta power of 2 power 1/2. So indeed, that term and that term will be A squared, and this term and this term will be R squared. So you will get R squared plus A squared minus 2AR cosine of phi prime sine of theta power of 1/2. Good. Perfect. Okay. So A of X is equal to mu0 divided by 4 pi IA integral of 0 to 2 pi d phi prime, then look at the expression for e phi prime. E phi prime, remember, is azimuth angle. What is the azimuth angle? It will be minus sine of phi prime x hat plus cosine of phi prime y hat. Do you agree? That's azimuthal angle. I mean, previously we did a calculation for one of the examples that we had. And denominator will be r squared plus a squared minus 2ar cosine of phi prime sine of theta, power of 1/2. Good. So then the vector potential has two components, x and y. All right? Agreed? Where is the point of observation? Remember, P is located in ZX plane. It is located in that plane, the green one that we plot here. And for that plane, we have vector potential which may have two components, along x direction or along y direction. Okay? So it will be mu0 divided by 4 pi IA. Then I have two terms, of course. So it will be x hat integral of 0 to 2 pi of d phi prime minus sine of phi prime divided by denominator power of 1/2 plus y hat integral of 0 to 2 pi of d phi prime cosine of phi prime divided by denominator 1/2. Can someone tell me what is the value of the first one? It is 0. It is 0 because if you look at the denominator, you have cosine of phi prime. You have to pay attention to both of them together. If you pay attention to this, you will find out that that is an odd function and in that domain, and that integral is equal to 0. What about the second one? So then A will have only one component, which is mu0 divided by 4 pi IA. Then I have a y hat integral of 0 to 2 pi of d phi prime of cosine of phi prime that's equal to r squared plus a squared minus 2ar cosine of phi prime sine of theta 1/2. That is changing from 0 to 2 pi. That is not easy to calculate, by the way, guys. It's a little bit tough. It can be expanding in terms of elliptic integrals. So and this is what people they obtain. So whatever is that value is a function of theta. Do you agree? Is a function of r, is a function of theta, is a function of a. So what you have the current multiplied by a, okay, or let's say in this way, f of r, a, and theta is not anymore function of phi prime because we are doing the integration on phi prime, and then we do have a long y hat. Okay. I just put the I because remember that's not geometric. This is related to the current that you have it in the loop. So what happens? Oh, sorry. You don't see the screen? No. Okay. So what happens essentially, if we have a loop of current, if we assume that's a Z plane, if we assume that that's X plane, sorry, a Z and X plane, then the potential, vector potential will be along this direction, right? This is what we obtain, is along Y direction, and that's the direction of Y. All right? Now, assuming that I am doing it for any arbitrary plane of Z and something else, I'm doing a full rotation, then what I'm expecting A to have? It will be I, f of R and A and phi, sorry, and theta, along the direction of phi. If you do a rotation, you will see that always that will be along azimuthal direction. That will be a vector that is showing along azimuthal direction. So essentially people, they write that simply that for the current that we do have in a loop, it will be, the only component that you do have is A phi. Okay, we will come back to this integral in a second and we will try to solve it in a different approach. But for the time being, remember that which component of the vector potential exists is A phi. Okay, is the only term. So A phi exists, and now we want to do the calculation finding out the magnetic field. How do we do the calculation? B is curl of A. If A has only A phi, because AR is equal to 0 and A theta also is equal to 0, and I'm using the curl in the spherical coordinates, then from the expression of the curl, I will be able to calculate the magnetic field. So essentially, magnetic field BR exists, which will be given by, I'm cheating, I'm looking at the expression for the curl, by the way. It's given by 1 divided by R sine of theta, derivative with respect to theta of sine of theta A phi. B theta is given by minus 1 divided by R, derivative with respect to R of R A phi. And also B phi is equal to 0, which is not surprising because that's the symmetry that we do have. So we find A phi, and as soon as we have A phi, we will take the derivative with respect to theta, we can take the derivative with respect to R, and we get the magnetic field, the component, the R component and the theta component of the magnetic field. All right? Is that clear? That is true, that is a ring. It sounds, should be simple, but it is not simple as someone may expect, because it, as I say, that it can be expanded in terms of elliptic integrals or elliptic functions. I think it's elliptic integrals, they call it, people. Yes, elliptic integrals of K and E. Well, interesting, but let's look at that. Physics is a field, is a science of approximation. This is the expression that we deal with. we were not able to solve it because, I mean, it can be given by integrals, and integrals you have to solve it numerically. But let's do something else. Let's do the approximation. So I'm writing down that expression down. So AFI is given by mu0 4 pi IA y hat. And then I have integral of 0 to 2 pi of d phi prime cosine of phi prime divided by r square plus a square minus 2ar cosine of phi prime sine of theta power of 1/2. Good. What I have to do? Again, look at the geometry. That's the distance of A. That's the point of observation. Can I assume that the point of observation is far away? There are several approximations that we may consider. One, R is close to 0. We are exploring that region. R compared to A is way, way smaller. So we are going inside that region, which is the green region. That's the first approximation. R is way, way smaller than A. Second approximation. Theta is close to 0. What does it mean? Sine of theta is close to 0. Okay. By the way, it should be sine of theta. Yes, that's correct. Okay. Sine of theta is close to 0. What does it mean? That theta, I'm assuming I'm doing the calculation for on axis. Fail. The third approximation that I can assume that R is way, way greater than A. This is what we call it the localized current, okay? And we can do all of those approximations. Which one do you want me to do? The last one? This is something that people always say like that. So let's go with that. So essentially, I have to look at the denominator, which is 1 divided by R squared plus A squared minus 2AR cosine of phi prime sine of theta power of 1/2. Then I assume that R is way, way greater than A, so I will factor out R, so it will be 1 divided by R. Then I have R is factor out. It will be 1 plus minus 2A divided by R cosine of phi prime sine of theta plus A divided by R power of 2 power of minus 1/2. Is that correct? I took away 1 divided by R square. 1 divided by R square goes away. It will be 1 divided by R power of 2 power of 1/2, which will be 1 divided by R. Then I will get the first term will be 1. The second term will be, second and last term will be the entire of these divided by R square. And then it will be power of 1/2, which I will bring it to the denominator, and that will be the result. So then approximately that can be given by 1 divided by R, 1 plus n, which is the power, it will be minus 2AR divided by R cosine of phi prime sine of theta plus A divided by R power of 2 minus plus minus 1/2 minus 1/2 minus 1, and then the other term, which will be whatever we have it in the expansions, power of 1 half, power of 2 plus the other term. I don't care about that, so it will be 1 divided by r plus 1 divided by r minus 2 goes away with a 2. It will be it will be 1 divided by r squared, or a divided by r squared, cosine of phi prime sine of theta plus the other term. Agreed? Is look like multiple expansions that we had previously as well. All right. So we can replace it inside of a phi. So a phi indeed will be mu0 divided by 4 pi ia y hat integral of 0 to 2 pi of d phi prime, and then I have 1 divided by r plus a divided by r squared cosine of phi prime sine of theta plus the other term cosine of phi prime. Good. There was a cosine of phi prime already. So what happens with the first term? It is integral of 0 to 2 pi of d phi prime cosine of phi prime 1 divided by r. That is 0, right? Because it's a cosine of phi prime. And the second term will remain, which will be a divided by r squared integral of 0 to 2 pi of cosine of phi prime power of 2 d phi prime. And then the entire of this is sine of theta plus the other term. That will be mu0 divided by 4 pi. That will be I a power of 2 y hat 1 divided by r squared. What is integral of 0 to 2 pi of cosine of phi prime power of 2? One half is a 1/2, right? Okay. And then we do have sine of theta plus the other terms. So indeed, that will be mu0. I will write pi a square I. Then here will be 8 pi square sine of theta divided by r squared. Okay, do you agree with that, guys? Beautiful. And that is essentially mu0 divided by 8 pi squared pi a squared I. I will call that magnetic dipole. Okay, I will call it M. And then I do have sine of theta divided by r squared. There is a y hat here as well, plus the other term. So that's based on approximation that we applied. Even we could start this from the beginning and going for 1 divided by x minus x prime and expanding them in terms of addition theorem, right? If you remember, that was given by spherical harmonics, or you can do it in terms of the Legendre polynomial because that's symmetric here in the calculation. So this is the way that you can do the expansions and you will get the potential. And now we do have a phi, which is explicit expression for that, and just you can place it here and you can get the magnetic field, because now it's just simply derivative with respect to theta or derivative with respect to r. And that's the approximation that we had it for the calculation of a phi. Is that clear? Beautiful. So I will stop here because I cannot finish the subject properly. So I will stop here. Next lecture will be about dipole moment as magnetic dipole moment, material, introducing magnetization, and then going and solving boundary conditions for different materials which they have different magnetic properties. And that will be the last lecture, I think. Okay? Any questions, guys? I will stop the video.
18th, I think.